Hey guys, welcome back. I hope you enjoyed your spring break. We're going to get right back into this. So this is a lesson that we're going to be doing in person. So if you're on the B schedule, no need to do this now. Just wait till Thursday until we do it in person. So 2 more weeks and then we're all back all 4 days. I will go ahead and warn you guys, if you notice, there's a lot of videos that I started doing on the fourth quarter of last year. And so once we get to those videos, I'm not going to have enough time to actually redo all those videos. So if you're learning from home, you're going to end up watching videos that I made from last year. Probably going to notice a little bit of a dip in the quality because I got a little bit better over the last year. So hopefully, perhaps you guys could actually come back and join us in person when we go back all 4 days. I would absolutely love that. So if you want any information about that, I can get that to you later. All right, so let's go ahead and get moving. So we want to, now that we've looked at proportions, one proportion z intervals and one proportion z test, now we're going to start comparing two different proportions. That's when it actually gets a little bit more interesting, I think. So we'll finish this unit pretty quick. This is our last chapter of this unit. Then we'll do the unit test, I believe, like in 2 weeks, so before the end of next week. So if we wanted to ask the question, are women more likely to buckle up? Well, there's two different populations we're talking about. We're talking about the population of women and the population of men. Perhaps we're restricting this to American men and American women more than likely. And those would give us two different proportions, two different sample proportions. So the question is if we look at the difference between those two sample proportions, is it a large enough difference that we measured in order for us to be able to say that women are more likely to buckle up or less likely to buckle up than men, or is it within the margin of error? And there would be inconclusive evidence suggesting there might not be a difference between buckling up between men and women, or if there is, that effect size is so small that with the sample size we had, we weren't able to detect it. In other words, it was within margin of error. So let's look and see what we have going here and see how we would, how our math would actually work out with this. So in 2007, the Massachusetts Traffic Safety Research Program found a proportion of 59% of males that were buckled up. If you want to read about this, study a little bit more. I think it talks about it in the textbook, so chapter 21, you can check it out yourself. So they took a sample of 6,971 males, and of those, 59% of them were buckling up. So our sampling distribution model, if it was actually centered at our sample proportion, we could find that standard deviation of 0.6%. Then out of 6,971 females, they found 70% of them were buckling up. So if you notice, that is a larger proportion than the males, and it would give us, I believe, a slightly, about the same standard deviation because it was the same sample size. All right, so here we have them side by side, a little bit easier to see what's going on here. So we got 6%, 0.6%, 0.6%, standard deviation is about the same. The difference is the proportions are quite different, right? So we're expecting 11%. It looks like 11% difference between our sample proportions with a standard deviation of 0.06. Now, the question that we have is when we subtract these two, we're going to subtract the female proportion minus the male because we want to deal with positive differences. And if it looks like the females are more likely to buckle up, we'll do female minus the male because we prefer to deal with positive differences instead of negative because they're easier to interpret. So if we look at this, the difference that we found between these two sample proportions was 11%. With a standard deviation of what? And that's really the question. So individually, they had a standard deviation of 0.6%. But those are going to be two independent events that we're adding together, so their variations would add together. In other words, their standard deviations will be added together by doing the Pythagorean Theorem, in other words. So going back to shifting and scaling and adding or subtracting random events, we need to remember that. So if we add a constant, like if I roll a dice, and I add a constant of 2 to whatever I roll, instead of having outcomes of 1 through 6, now I would have possible outcomes of 3 through 8. So all we did is we added 2 to the expected value. The mean got shifted over to the right 2. The standard deviation remained the same because it's the same spread. It's just shifted. So the variation would be the same as well, which would be the standard deviation squared. Now, whenever we multiply, so if I take a dice and I roll it, and then I double the amount of points that you get, now, instead of going from 1 to 6, the smallest we could have would be 2, and the largest would be 12. So our center, the mean, would be multiplied by 2 as well. So it's doubled. Now our average would be 7. The standard deviation is going to be doubled as well, which means the variation would be multiplied by our constant squared, or a squared, and whatever. That's where the a squared comes in. So that would be 4 times the variation of what we had before. So what about adding or subtracting two random variables? So like if we took 2 dice and we added or subtracted the difference between those two dice, we're going to end up adding the independent each individual expected values. So that part's pretty simple. But now they're going to start basically kind of I guess canceling each other out. So some of them could be larger than what we expected, some would be smaller than we expected. And so if we start adding those together, we start getting this triangular distribution, which we've talked about quite a bit up to this point, where still we're expecting an average of 7, 3.5 for each dice would be 7. Our standard deviation is not going to be doubled anymore. This is actually going to be done by the Pythagorean theorem. So 1.7 squared plus 1.7 squared, and then we take the square root of that. Now the variation, if you notice, is going to be is actually going to be added together. So 2.9 plus 2.9 will give us 5.8. So we take the variation from one dice plus the variation of our second independent event, which is the second dice, and we would add them together. Even if we're subtracting these, like if I take this over here, I don't think I have it set up to show you that, but if I take this distribution of all these, the triangular distribution, and then shift it all to the left, start at 0, that would be the expected difference between the two. It's still the same distribution, except some of them are negative and some of them are positive. So the whole thing would just be shifted over to the left by 3.5 or by 7. So here's our Pythagorean theorem. The Pythagorean theorem states that if a and b are perpendicular, in other words, if this is a right angle, then the a squared plus b squared is equal to c squared. So if you notice, we take the length of 3, we square it, this squared plus this squared is equal to this squared, which is kind of cool. Pythagorean theorem. So the Pythagorean theorem of statistics says that if a and b are independent events, then the standard deviations are like the legs. So 3 squared plus 4 squared would be equal to 5 squared, which is the sum or the difference between those two independent events. So in other words, whenever we're squaring these together, when we square the standard deviations, that is the variation. So in other words, the variation of A plus the variation of event B add together to give us the variation of the sum of those two events A and B. So let's go back to our example before. We had two independent proportions. So we had our sample proportion of females and the sample proportion of males. Both of those had a standard deviation of 0.06%. So what we would end up doing is basically this value squared plus this value squared, and then we take the square root of it, which would give us the basically the Pythagorean theorem of statistics of the standard deviation of the sum or the difference between those two events. So the difference between these, so the sample proportion of the female minus the proportion of males that are buckled is 11%. So that would be 11% here with a standard deviation of that. So the difference we observed, if it was actually 0, is going to be way, way up here, which is basically not going to happen. So our p-value is, because the z-score is way, way up there. So we can actually do all of this in a calculator. So we're going to go to stat, arrow over to test. Instead of doing a 1 proportion z-test, we're going to do a 2 proportion z-test because we're comparing two different proportions. So the x1 is going to be from the first proportion. So that's the total number of successes we had out of the first one. So if we're doing, we're going to do females first. So that's going to be 0.7 times the total that we had, which was 6,971. And remember, that's going to be a rounded value. So we want to go ahead and change that, round it up here. Okay, so it's going to be 4,880 women who were buckled up out of a total of 6,971 drivers. And then the same thing for the men. So that value times 6,971, and then that's going to be rounded as well, out of a total of 6,971 male drivers. Now our hypothesized proportion is going to be that the first proportion is larger than the second proportion because we did the female larger than the male. So that would be there, and then we're going to hit calculate. So this is a z-score of 13.57 standard deviations above the mean. So let me actually go back to this one over here. All right, so the probability of observing a difference of 11% when we're expecting 0, right, that would be our null hypothesis, is going to be 13.57 standard deviations above the mean. So that's basically not going to happen. The probability of that occurring is 2.9 times 10 to the negative 42nd power, meaning there's 41 zeros in front of that. Essentially, that's not going to happen at all. So let me show you what this looks like with the Pythagorean theorem. So basically, we have two proportions. We have a proportion of females and the proportion of males. When we added these together, they're basically two independent events. So it's going to look like the Pythagorean Theorem statistics. So we have a squared plus b squared is going to be equal to c squared. Then over here we have the difference between those two events. So basically we have a standard deviation of 0.6%, standard deviation 0.6%, and then together by doing the Pythagorean theorem we have a standard deviation of 0.85%. So that's a standard deviation we'd expect for the difference. Now we had a difference observed of 11%, which is like we said 13.57 standard deviations above the mean, which is incredibly statistically significant. It's, which would be overwhelming evidence to suggest that women are more likely to buckle up than men. Now the actual proportion that we believe that would come from a confidence interval, which is the percent that the difference between the men and the women buckling up, which is centered around 11%. So what is that sample proportion? Which is the next logical question. Now that we've rejected the null hypothesis in favor of the alternative, we believe there is a difference. Then what do we think that the proportion of the difference between women and men buckling up? So to do that, we would go to stat, test, and then towards the bottom, I believe, two proportion z interval, and then that basically is already the same thing we had there. And then our confidence level, we can do 95% confidence if we want, then hit calculate, and that's going to give us a difference of between the two proportions anywhere between 0.93. I guess that's slightly different. I must have done 90% confidence on this one, or my numbers were slightly different. I'm not sure, I'd have to check, but you get the idea. You can do a 90% confidence, 95%, or 99% confidence interval on these. And also, if you're looking at our confidence interval, since 0 is not contained in this, we would have enough evidence to reject the null hypothesis and say that we believe there is a positive difference between the number of women who buckle up and the number of men who buckle up. All right, so the last thing I wanted to show you is kind of a corollary that falls from this the book gets into. So the question is asked is that, do men behave differently when women are around, which is kind of funny. So if your mom's in the car, are you more likely as a man to buckle up than if your mom was not in the car? I think this is true. Also, if you are just riding around with your guy friends, you're probably less likely to buckle up as if you are driving around with your girlfriend or any female in the car, even if it's not your mom or girlfriend, whatever. All right, so they looked at a study and they said when men are with other males, they found this proportion that buckled up, but when there was a female in the car, they found this proportion of men were buckling up. So they looked at basically, I think people driving on the highway, and they looked at who was in the car from what you can see from the cameras, and then whether or not they were buckling up. All right, so the difference between these two, with the female in the car or without, is a difference of 16.7%. The only question we have now, even though it looks like there is evidence that they are more likely to, is that statistically significant? So is 0 within two standard deviations, in other words, or whatever our z-score or p-value is going to be from that. So we have two different standard deviations. So we would take our p hat times q hat. That would give us, then we divide it by our sample size and take the square root of that, which gives us a standard deviation of basically 0.7% for if there's a female in the car. Then for the males, you do the p hat times q hat divided by the sample size, which is a much smaller sample size, which means this is going, and you take the square root of it, which means it's going to have a much larger standard deviation of, well, 0.9%, not that much larger, but it is larger. And then the last thing we do is do the standard deviation, the Pythagorean theorem. So we basically square their standard deviations and then take the square root of it when we're done, which will give us the the standard deviation for the difference of these two, or the sum of these two random events, which would be basically 1.2%. So then the only question we have left, even though we have an observed difference of 16.7% of men buckling up when there's a female in the car versus when there's no female in the car, what was our standard deviation? Well, we said our standard deviation was 1.2%. So that is going to be well beyond 10 standard deviations, which is going to give us basically a p-value of 0, which is very strong evidence for any reasonable alpha for us to be able to reject the null hypothesis in favor of the alternative. So if we wanted to actually put this in the calculator, we actually could do that as well if we wanted to. But basically kind of showing you how the math would work for the standard deviation between the two. You take the standard deviation for with the females squared plus standard deviation for the males squared. Then we take the square root of all that, which is how we got the 1.2. Visually, it kind of looks like that with the Pythagorean theorem. So that's what our sampling distribution for the difference of those would look like. The main thing that you need to remember from this is we're using the Pythagorean Theorem of statistics. So whenever we are basically adding random variables, if they're independent, we add the variation of the two. So the variation of the sum, or the difference between two random events or two proportions, in this case sample proportions, are going to be the sum of the variation of the two. Or if we're dealing with standard deviation, we have to do the Pythagorean Theorem of statistics. All right, so that's what we need to remember for the new stuff today. So the sampling distribution of the difference between the two proportions is found basically by taking the square root of the standard deviation of the two, right? So whenever we square the square root, it kind of goes away, and that's why it looks like this. But this is basically going to be the standard deviation of the first proportion without taking the square root, because we squared the square root and they went away, plus the standard deviation of the second proportion, of course without the square root because we squared it, and then we take the square root of the whole thing. So that's what it looks like, but pretty much you're just going to be putting in the calculator for the most part, so no big deal. Whenever we're doing a two proportion z interval, that's done by the calculator as well, but it's basically just some critical value times the standard error of the two, which that formula was found on the last slide. So we take the difference that we find between them, plus or minus a margin of error, which is their critical value, which is basically going to be how far we have to go out in order to capture a certain proportion, or a certain percent of the data between the two. So let's go ahead and start the assignment with number 12. So buy it again. A consumer magazine plans to poll car owners to see if they're happy enough with their vehicles that they would purchase the same model again. They'll randomly select 450 owners of American-made cars and 450 owners of Japanese models. I will point out it's not important to have the same number of both. It just means with a smaller sample, like if we only did 200 Japanese car owners or whatever, then owners of Japanese models, you know what I'm trying to say. Then that would just mean it would have a larger standard deviation, which is not that big of a deal. So I'm just going to point that out. Obviously, the actual opinions of the entire population can't be known. So let's suppose that 76% of owners of American cars are satisfied that they would buy them again, and 78% of owners of Japanese cars would purchase them again. So what is a sampling design? What sampling design is the magazine planning to use? All right, so on this one, we're assuming it's a random sample. Did it say that? Okay, so they're going to randomly select 450 owners of each type of car. So this is actually a stratified sample because they're fixing it so that we are doing the same number of each, or sometimes they do that in proportion to the actual number. So like if you have more freshmen than you have seniors, then they want to make sure that they have the same amount, or the correct proportion of seniors that are being polled and the correct proportion of freshmen being polled as well. So different things that they do. The other way you could do it is, of course, by weighting them by their respective proportions, which is how you do it. So you do like a weighted average. But anyway, this is a simple random sample. It's a stratified simple random sample, stratified by the origin, the car's country of origin. What difference would you expect? Well, if there's actually 78 and 76, there's a 2% difference between the two. So we would expect that they would differ by 2%. So if we did the proportion of Japanese minus the proportion of Americans that were satisfied with their car, that type of car or whatever, then there would be a positive difference of 2%. So of course, sampling error means that the poll won't reflect the differences perfectly. We know each sample is going to have a variation from sample to sample. So the standard deviation is going to be given by the actual proportions, the population proportions, but the standard error is going to be based on the actual sample proportions that we get. Now in this case, they told us the actual population proportions, and so we could actually calculate this. So what's the standard deviation for the difference in the proportions? So I'm going to put this in the calculator. So I'm going to do the square root of, and then I'm going to do alpha x so we can put it in as a fraction. But we said for the Japanese it was 0.78, so that would be p times q of 0.32 divided by 450, our sample size. And then I'm going to arrow over, but not outside of that. So that plus, then I'm going to do alpha x again to put it in as another fraction. And this one's going to be 0.76 times 0.34 divided by 450 again as well. Okay, so again, it's not important that these are the same numbers. They just did it in this case because it was a stratified sample. All right, so that's going to be it. That's going to be the standard deviation of the difference between the two. Then sketch a sampling distribution model for the difference. So we would expect a difference of 2% with a standard deviation of that value. So just add that. So basically 0.02 plus this value, and then do it again. So that plus that value again, and you get it. Then you can subtract that value going the other direction. So go 2 in both directions, and we'll call it good. All right, could the magazines, well, that's what this is, by the way. So could the magazines be misled by the poll, concluding that owners of American cars are much happier with their vehicles, or just more happy with their vehicles than owners of Japanese cars? So that would be when the difference in the proportions was negative, because the American would be higher than the Japanese in that case, which would be the wrong conclusion. So that would happen anytime that we would have a negative proportion. So that's with the z-score here, that would be to the negative. Now that's going to be within one standard deviation of the mean. So because our sample size are so small and the effect size between the actual proportions are so small, it's only 2% difference. So basically it'd be very common for us to commit this type of error, which would be that we would reject the null hypothesis in favor of the alternative and saying that there was actually evidence that that people preferred American cars over the Japanese cars. And so that would be a very common mistake for us to make. Number 14, graduation. In October 2000, U.S. Department of Commerce reported results of a large-scale survey on high school graduation. Researchers contacted more than 25,000 Americans aged 24 to see if they had finished high school. So that percent of males and that percent of females indicated that they had high school diplomas. Are the assumptions and conditions for inference satisfied? So our 10% condition, we know we're sampling without replacement, so as long as we're sampling less than 10% of the overall population, it's not going to change our overall final conclusion. So in this case, we are sampling obviously less than 10% of all males and females in the US, so that's totally fine. Independent group assumption. So now that we actually have, this is a new condition that we have, if we're looking at two different groups or two different populations, like male or female, we have to be able to assume that those two groups are independent of each other. So is there any reason to believe that they would be tied together? So for instance, if a male graduates, does that mean that it's more likely for a female to graduate? Since those males and females are not tied together in any way, then they should be independent. So it's reasonable. Groups are independent of each other because it's a simple random sample. So if we actually like pair them together, which we'll talk about paired data later, but like if we chose like if there was a sibling, so like a brother and a sister, if the brother graduates, it's probably more likely that the sister graduates as well. So there could be some associations between those two, but as long as we're randomly selecting them, not selecting all of our males and then looking at their sisters or whatever at the same time, then we'd have some sort of association. So the simple random sample is going to basically alleviate any issues that we would have between any sort of association between those two groups. So we're not selecting them in pairs or anything like that by relationship or anything like that. You also would have issues like with husbands and wives and things like that. So any way that the two groups could be related to each other, we need to be careful of that. All right, randomized condition. So they were random samples, so they should be representative of the overall populations. Success failure condition, we had obviously at least 10 people that did and didn't graduate from both groups. So create a 95% confidence interval for the difference between the males and females. So I'm going to go back to this slide so I can actually see the data as I put it in the calculator. So on this one, we're going to go to stat test. They wanted a confidence interval, so we're going to do a 2 proportion C interval. So the first one we had, actually it doesn't matter which one I do because I can just select that one. Okay, so I'm going to do 0.849 times the number of males. All right, then since that was rounded, we want to go ahead and round that back up. So round that to the nearest whole because we can't have 0.4 or 0.54 males out of a total of 12,460. And then for the females was 88.1. And again, we want to round that. I'm going to round this one down. All right, they wanted a 95% confidence interval, I believe. All right, so there's our 95% confidence interval. All right, so if you look at the difference between these two, it's going to take the first proportion minus the second one, which would give us a negative value, meaning the second one was smaller, or sorry, the second one was larger, and the second one we put in was the females, I believe. So we noticed that females were more likely to graduate, and that's why we had a negative value here. You could put the females in for the first proportion and the males in for the second, then you get a positive difference. So just be careful of that. Since 0 is not contained in this confidence interval at all, we would actually have enough evidence to reject the null hypothesis that there was no difference. We actually do have enough evidence to suggest that women are more likely to graduate than men based on these sample proportions. So interpret your confidence interval. So we're 95% confident that the true proportion of females that graduate more than the males is between 2.3 and 4%, which is exactly what we saw here. So 4% and 2.3%. Okay. Does this provide strong evidence that girls are more likely than boys to complete high school? Yes, because 0 is not contained in this confidence interval. It's not within the margin of error, so we don't think it's possible that there was no difference between the two. So we have enough evidence with a 5% alpha level to suggest that women are more likely to graduate high school than men. All right, so that's all I'm going to do with you. I think the rest of all the questions are odd, so you can use the back of the book to check your answers. If you have any questions, please make sure to let me know, and I'll see you guys later.